Deep beneath the English Channel, two tunnelling crews were moving towards one another through solid rock. One had started in Britain, the other had started in France. Neither could see the other, hear the other, or receive a position from the surface. Above them were the seabed and millions of tons of seawater. Around them was darkness, chalk, and a tunnel stretching kilometres back to land. If you want more stories of engineers pushing machines through impossible ground, subscribe to Industrial Empire. If either crew had followed an alignment that was wrong by even a tiny fraction of a degree, that error would have grown with every metre they excavated. The tunnels could have passed beside each other. One could have gone over the other. After years of construction, the two countries might have ended with separate dead ends beneath the sea. Then, in October 1990, a small British probe drilled into the rock ahead. On the French side, the approaching crew detected it. The two underground routes were finally compared. After driving from opposite countries, their calculated positions differed by just 358 millimetres horizontally and 58 millimetres vertically. That extraordinary accuracy was not a lucky final correction. It was the result of an invisible engineering system that had been guiding the machines from the moment excavation began. But making the two sides meet was only one part of the problem. Before engineers could connect Britain and France, they had to find a layer of rock capable of holding back the channel, build machines that could survive radically different ground conditions, and decide what to do with 11 enormous tunnelling machines when there was nowhere for most of them to emerge. Plans for a tunnel beneath the channel had existed for nearly 2 centuries. Some were serious engineering proposals, others looked more like science fiction. Submerged tubes resting on the seabed, artificial islands in the middle of the channel, and tunnels illuminated by oil lamps so horses could pull carriages between countries. The distance was not the only obstacle. The channel is one of the busiest shipping routes in the world. Any fixed structure rising from the water could interfere with ships. A tunnel avoided that problem, but replaced it with something more unsettling. A leak beneath a river might allow workers to escape through a nearby shaft. A major leak beneath the channel could occur kilometres from land, with no direct route to the surface and an almost unlimited supply of water above it. The success of the project would therefore depend on what lay beneath the seabed. Over decades of surveys, engineers drilled exploratory holes and mapped the geological layers between Britain and France. They were searching for chalk marl, a material soft enough for a machine to excavate, strong enough to support a tunnel, and, most importantly, relatively resistant to water. But this layer was not perfectly level. It dipped, curved, and changed character as it crossed the channel. The shortest route between the two countries was therefore not automatically the safest. The tunnels had to descend from the coasts, enter the chalk marl, and follow it beneath the sea. This is why the Channel Tunnel does not travel in a perfectly straight horizontal line. The route follows geology rather than geometry, and it is not actually one tunnel. The completed system contains 2 large railway tunnels with a smaller service tunnel running between them. Cross passages connect the service tunnel to both railway tunnels at regular intervals, creating access for maintenance and a protected escape route during an emergency. That smaller central tunnel was also the first one excavated. This was a crucial decision. Instead of committing the 2 large railway tunnels to ground that engineers had only studied from the surface, the service tunnel advanced ahead of them as an underground reconnaissance mission. It revealed the actual condition of the chalk, exposed wet or fractured areas, and allowed information to be passed to the crews driving the railway tunnels behind it. If the service tunnel encountered a problem, the main tunnels would receive warning before reaching the same location. Construction began from both countries because excavating the entire crossing from one shore would have taken far too long. 6 tunnel boring machines began from the British side, while 5 operated from France. Together, they had to excavate the service tunnel, the 2 railway tunnels, and the landward approaches. A tunnel boring machine does far more than carve out a circular hole. At its front, a rotating cutterhead presses tools into the rock and breaks material away from the face. The excavated chalk passes backwards through the machine, while an industrial train of equipment follows behind. As the machine advances, crews install curved lining segments around the newly exposed tunnel. These segments form complete structural rings, preventing the ground from closing around the machine and isolating the finished tunnel from water. The cutting, spoil removal and lining installation must proceed as one continuous operation. If excavated material cannot be removed, the machine stops. If lining segments do not arrive, the machine cannot safely expose more ground. A TBM may be the most dramatic object underground, but its progress depends on an entire factory stretching behind it. And the two sides of the channel required very different factories. The chalk beneath the British side was generally drier and easier to excavate. British machines could operate with a more open cutting face, allowing broken material to move away efficiently. The French side was wetter and geologically less consistent. There, machines required greater protection against water entering through the face. Excavation was slower, and the equipment had to manage wet spoil under pressure. This difference affected where the two sides would eventually meet. Because the British machines advanced more quickly, they excavated more than half of the undersea distance. Even the unwanted rock was handled differently in each country. On the French side, excavated chalk was crushed, mixed with water and pumped inland behind a specially constructed dam 37 metres high. In Britain, millions of tons of chalk were carried out beneath Shakespeare Cliff and deposited at the coast. That material created a new piece of land rather than being treated simply as waste. It was landscaped and eventually became the area now known as Samphire Hoe. The tunnel was literally creating new land as it disappeared beneath the sea. But no matter how powerful the machines were, none of them knew where France or Britain was. Underground, there was no view of the horizon, no satellite position, and no opportunity to drill a vertical shaft every few kilometres to check the route. The machines could only follow the alignment transferred to them by surveyors. Before excavation reached the channel, teams established extremely precise reference networks on the surface. Known points on both coasts had to be related to the same geographical system. Their positions, elevations and angles formed the starting truth from which every underground measurement would descend. That alignment was then transferred through the access shafts. Surveyors used plumb lines, optical instruments, precise levelling and gyroscopic measurements to carry direction underground. Inside the tunnel, reference points were installed behind the advancing machine. Lasers projected the intended route forward, while sensors measured the machine's position, pitch and direction. The operator could then steer by making minute changes to the forces pushing the machine forward. But there was a dangerous weakness in this system. Every new underground reference point depended on the accuracy of the points behind it. A small mistake would not necessarily look dramatic near the coast. The laser could still appear centered, the tunnel could still look straight. Yet over tens of kilometres, an almost invisible angular error could become a miss measured in meters. And there was another complication. A TBM does not behave like a drill passing through a rigid block of wood. It is an enormous moving structure pressing against natural material. The rock changes, cutting forces change, the machine can roll, rise or drift sideways. Surveyors therefore could not establish the route once and walk away. They had to measure repeatedly, compare independent observations and check whether the machine's real movement matched the intended alignment. This created two parallel construction projects. The first was visible, machines cutting chalk and workers installing concrete and iron. The second was almost invisible, a chain of measurements stretching from surface markers in two countries to reference points deep beneath the channel. If the first project failed, the machine would stop. If the second failed, the machine might continue perfectly in the wrong direction. By 1990, the British and French service tunnel drives were approaching the planned meeting area. At this stage, allowing two full cutterheads to simply crash through the remaining rock would have been reckless. Engineers needed to know their exact relative positions before opening the connection. A smaller British probe was driven ahead through the chalk. On the French side, workers detected its arrival. For the first time, the two independently constructed tunnels could be compared physically instead of only on plans. The result was remarkable. After kilometres of excavation from opposite shores, the alignment differed by 358 millimetres horizontally and 58 millimetres vertically. The discrepancy was smaller than the tunnel itself by an enormous margin and easily manageable within the final connection. There was no second tunnel hiding somewhere beside it. No machine had passed beneath the other. The surveying systems established in Britain and France had arrived at almost the same point beneath the sea, but the probe created only a small opening. It proved that the routes had met. It did not yet allow people to cross. The remaining chalk was carefully removed until, on the 1st of December 1990, British tunneller Graham Fagg and French tunneller Philippe Cazette met through the service tunnel. For the first time in thousands of years, a person could cross between Britain and continental Europe without travelling through the water or over it. The breakthrough photographs showed cheering workers, national flags, and two crews shaking hands. But the most important object in those images may be the rough edge of the opening around them. That broken circle was the physical proof that thousands of measurements taken over several years had agreed, and the breakthrough delivered another payoff. Because the service tunnel had been driven ahead, its successful connection confirmed the alignment before completion of the two larger railway tunnels. The main machines continued towards their own meeting points using the same survey network. Their breakthroughs completed the basic underground route, but there was still an enormous amount of work before a train could enter. A TBM produces a lined passage. It does not produce an operating railway. Crews had to install track, electrical power, drainage, communications, signalling, ventilation, fire protection, and the equipment required to manage pressure created by fast-moving trains. When a train enters a long, narrow tunnel, it pushes air ahead like a piston. Without somewhere for that pressure to escape, passengers would experience stronger pressure changes and trains would face greater aerodynamic resistance. Large relief ducts were therefore constructed between the two railway tunnels. As a train pushes air through one tunnel, part of that pressure can pass through the ducts into the other. The service tunnel also had to become a functioning safety route. Special vehicles could travel through it without interfering with railway traffic. Cross passages allow people to leave one railway tunnel and enter the protected central bore. Fire doors, ventilation controls and monitoring systems turned the three separate holes into one coordinated system. Heat presented another problem. Trains, electrical equipment and aerodynamic friction would continuously warm the enclosed environment. A vast cooling water network was installed to keep tunnel temperatures within safe operating limits. Even the crossover caverns were enormous engineering projects. These underground chambers allowed trains to move between the two railway tunnels when necessary, but they were far wider than the ordinary bores. They had to be excavated and supported without compromising the surrounding chalk or the service tunnel that provided access to them. Meanwhile, the tunnelling machines themselves faced a final problem. A machine hundreds of meters long cannot be turned around inside an ordinary tunnel. Bringing every British machine through to France would interfere with the French drives, while dragging them backwards through kilometres of completed tunnel was impractical. For several of the British undersea machines, the solution was to steer them down and away from the final tunnel alignment. They excavated their own burial positions inside the chalk and were left beneath the channel. The French machines then completed the remaining connections and were dismantled. Parts of the equipment were recovered, but some of the machines that created the crossing never left it. They remain outside the operating tunnels, entombed in the same geology they were built to excavate. Once the construction equipment was removed, the lining completed and the railway systems tested, the Channel Tunnel officially opened on the 6th of May 1994. The finished route extends approximately 50 kilometres, with about 37 kilometres running beneath the sea. Still the longest undersea section of any tunnel in the world. But its most impressive measurement may remain the smallest one, 358 millimetres horizontally, 58 millimetres vertically. Those figures represent the difference between two surveying systems that began in separate countries, travelled down different shafts, passed through kilometres of darkness and guided enormous machines towards a point no worker could see. The cutterheads supplied the force. The concrete rings held back the ground. The service tunnel revealed what lay ahead. But the connection between Britain and France ultimately depended on something far less visible, a continuous chain of measurements accurate enough to make two countries meet beneath the sea.